Good morning and afternoon to everyone. I'm delighted to welcome you to our continuing webinar series at the intersection of AI and geosciences. I'm Hal Green and I manage marketing for Geophysical Insights, the sponsor of today's webinar. For those of you that don't know Geophysical Insights, we develop and market the Paradise AI Workbench, your guide to reservoir characterization. You may have seen our tropical theme Paradise booth at conferences worldwide. However, today's talk by Roden will not focus on one technology, but rather be a survey of several technologies that are affecting our industry. Momentarily, Rocky will address the impact that AI is having in our industry currently and just over the horizon, particularly on exploration and field development. This is a timely topic, of course, as we see the adoption of large language models like ChatGPT and AI agents. Rocky's talk will address these innovations, fit-for-purpose geoscience applications of machine learning and deep learning technologies, and how AI is transforming geoscience workflows. I'm in Houston, Texas, and Rocky is in Centerville, which is midway between Dallas and Houston. When he's not consulting and finding hydrocarbons for his clients, Rocky runs a ranch in Centerville, and you will see in the background a nice view of his ranch from a drone view that he's taken at some point. So we welcome your questions, by the way, via the chat feature in Teams. If your question relates to a particular slide, please try to reference that slide in your question, and perhaps Rocky can go back to that slide. Now, I am delighted to say a few words about our speaker before we get started. We're delighted to have Rocky Roden again with us today. I think the last time he presented at one of our webinars was in March of 2023. Our guest is a prolific author and speaker while consulting for E&P companies on both sides of the Atlantic. Rocky started Rocky Ridge Resources in 2003 and works with several oil and gas companies on technical and prospect evaluation issues. He is, in addition to being an advisor to Geophysical Insights on our technology direction, he's a principal in the Rosen Associates DHI Risk Analysis Consortium, where he is a senior advisor to many companies. Rocky is a proven oil finder with 47 years in the industry, combined with an extensive knowledge of modern geoscience technical approaches. He holds a Bachelor of Science in Oceanographic Technology and Geology from Lamar University, and a Master's of Science in Geological and Geophysical Oceanography from Texas A&M University. As Chief Geophysicist, now retired, and Director of Applied Technology for Repsol YPF, his role there included advising corporate officers, geoscientists, and managers on interpretation, strategy, and technical analysis for exploration and development in offices in the US, Argentina, Spain, Egypt, Bolivia, Ecuador, Peru, Brazil, Venezuela, Malaysia, and Indonesia. He has been involved in the technical and economic evaluation of Gulf of Mexico lease sales, farm outs worldwide, and bid rounds in South America, Europe, and the Far East. Previous work experience includes exploration and development at Maxis Energy, Pogo Producing, Deca Survey, and Texaco. Rocky is a member of the SEG, AAPG, Houston Geological Society, the Geophysical Society of Houston, EAGE, and CITES. He's also a past chairman of the Leading Edge editorial board. Now, I'll turn the screen over to Rocky and we'll get started. Thank you.
Well, I want to thank everyone for listening in today to this presentation. And this is not a real detailed presentation. It's kind of a view of technology trends that I think are evolving and something that we all need to be aware of and And it's pretty exciting, actually, once we get into this. And what I'm going to talk about first is just a very general, basic description of artificial intelligence and machine learning, especially as it relates to geoscience applications. And then I'm going to go over a couple of slides on kind of where we are as an industry in using various machine learning applications and how we're using those, at least from an interpretation perspective. And then the use of machine learning in something full waveform inversion. A lot of you may have heard about this, but the potential is there to have a significant impact on our industry in the future. And I'll go over that and let you make your own opinion on that. And then finally, what drives all of these applications is computer power and where that's going and how that's evolving and its potential impact on all these technologies. So first of all, I'm just going to go through understanding the scope of artificial intelligence and machine learning, because a lot of these terms are used. You hear it every day, and it's sometimes quite enlightening to see kind of what are we talking about? Is it all hard to understand? Is it all straightforward? Well, hopefully I can make that a little bit more understandable. Now, in data science, we have several categories of data science. And of course, artificial intelligence is the big one. And that's kind of the overriding category. And it's any technique that enables computers to mimic human behavior. Subset of that, which is most of the applications we're dealing with, are machine learning. And these are techniques that give computers the ability to learn without being explicitly programmed. And of course, a lot of what we use are neural networks. And these are algorithms that process signals through these nodes we call neurons, which are simulations of the human brain. And deep learning is really nothing more than a subset of these neural networks where there are multi-layers of these neurons. And in today's world, usually if you have more than 3 layers, they say that's deep learning. A lot of computations, in other words. Something that's been around for actually more than a decade is something called generative AI, which it creates new content based on prompts and learns patterns from the data and generates original outputs. But what's really focused in on that the last 2.5 years since ChatGPT came out are these large language models. And they're a subset of this generative AI, and it's designed to understand and interpret human language. I'm not going to go into detail on that, except at the very end, I'm going to show you how I think it fits in the future. So what are the general types of machine learning that we're talking about being used? Well, supervised learning, unsupervised learning, semi-supervised, and reinforcement learning. These are the 4 fundamental types of machine learning. And supervised learning is kind of a task-driven. In other words, I know the answer to a certain situation. I develop labels or descriptions. I develop a model that gives me the answer I want, and then I apply it to a set of data that I don't have that answer. Unsupervised learning is very, very different. Unsupervised learning knows nothing about your data. It looks at the data, it identifies the natural patterns and clusters and how they relate to each other in some cases. In today's world, semi-supervised learning is nothing more than a combination of supervised and unsupervised, however it's applied. And then reinforcement learning, where you learn from your mistakes. These are kind of the broad categories of machine learning. Now, I know I can't get answers to everybody, but here's a test. You thought I was going to let you off without having some input. I know you can't answer this, but look at these sets of numbers and tell me, I know you can't tell me, but just think, what is the answer to where I have the question mark? That's pretty straightforward. Well, hopefully you got 81. If you got that answer right, then you have successfully accomplished supervised learning. So how did you do that? Well, you looked at these numbers You saw the numbers on the left. You saw that if you square them, you got the numbers on the right. So you built a model, applied it to 9, and there you got 81. That fundamentally is supervised learning. You're building a model and applying it to get the answer. Now, there are fundamentally two types of supervised learning, classification and regression. Now, typical regression, is nothing more than fitting a line to a set of data to understand how it's distributed. As you can see right here, very straightforward, whether you're using linear regression, multiple linear regression, you're fitting these lines to fit the trends in the data. Now, if you look on the left in classification, you're doing very similar sorts of things you're doing with regression, only now instead of fitting a line or a plane that shows the trends, you're separating this into different classes or groups. Now, these two approaches that I've just talked about with these descriptions here, these are traditional machine learning-based linear understandings and predefined statistical models. These have been around for decades. A lot of you I know were using some of these long before we ever knew much about machine learning. But these basically are fundamental from the standpoint that they require linear trends and normal distributions for most of these approaches. Neural networks are very different. These are not neural networks. Neural networks, as we're going to talk about, are very different. They can handle linear trends in the data and non-normal distributions. That's the power of neural networks. Okay, I have another test here. This time you have 6 objects here. And I want you to look at these objects and determine how many patterns or clusters can you identify in these 6 objects. I know it may take you a while to look at that, but here's one of them, is shapes. Something round versus box shape. There we have different fruit and non-fruit, different colors, variations in colors. Well, if you did that, then you successfully accomplished unsupervised learning. All you did was look at the data, didn't know anything about it. You just looked at it, identified the natural patterns or clusters in the data. And that fundamentally is unsupervised learning. Pretty straightforward. Now, in unsupervised learning, fundamentally, you're looking at clustering or looking at pattern recognition. And clustering is commonly used for data exploration, anomaly detection, and data mining. Kind of sounds like exploration, or exploration for oil and gas. And there are several sorts of clustering techniques. A common one is self-organizing maps, which is a neural network. It's an unsupervised neural network. K-means is actually very similar to that. However, in the self-organizing maps, when it defines these patterns or clusters, it also tells you about how they relate to each other in a topology. That's extremely important when we're talking about geology. Extremely important. Now, there's also something called dimensionality reduction. And what that tries to do, it reduces the number of irrelevant or random features in a whole bunch of different types of data. And these are things like principal component analysis or independent component analysis. They try to reduce those numbers or irrelevant features, get it down to a more feasible amount that still represents the overall trends in the data. So this is unsupervised learning. Now, in geoscience, we know that we are deeply grounded in physical laws and principles discovered over multiple centuries of systematic research. Here's 4 of these scientists you can see here of many have developed these laws that we go by. And geoscience features have space and time relationships. They're highly multivariate. They follow nonlinear trends, non-stationary characteristics, and they often involve rare but significant events. This is why a lot of our machine learning, their algorithms that are only based on statistical approaches and linear approximations, sometimes they don't fit what we're looking for in our geology. This is where neural networks come in. And as we know, the neural networks are a computational simulation of biological neural networks. And they have several advantages over these non-neural network approaches that rely on predefined mathematical models. These neural networks can learn complex nonlinear relationships. And a tremendous amount of what we're trying to interpret in geology are nonlinear relationships. That's why they're hard to interpret in a lot of cases. High dimensional data sets it can handle. In other words, a lot of different types of data. It excels at unstructured data. Most things in nature are not normally distributed. They're log normal, they're betas, they're reverse log normal, they're uniform. They're all sorts of different distributions in nature that are not normal. So we need something that can handle that and see those sorts of things. And it can obviously handle very complex problems. So that's kind of just a general overview of artificial intelligence and specifically machine learning. But how are we using that in our industry? How are we using artificial intelligence and machine learning to find oil and gas? Well, there was a paper that came out this year in Geophysics. It's a very good paper by Anjom et al. And what they did is they looked at all of the papers that were published in the SEG and the EAGE from 2010 to 2021 that related to machine learning and artificial intelligence. And as you can see in the blue, nothing really happened until after 2016. And I can tell you that this is true because in 2016, I was with Geophysical Insights at the EAGE convention in Vienna, and nobody had a clue what we were talking about. There was not another booth talking about it. I didn't see a single technical paper on machine learning. And of course, after that, it started to take off. And you can see in some other databases that relate to all the other scientific fields and disciplines, they started taking off a little quicker than we did. Now, this is also some of the results for Anjom, and what you're looking at here. He actually looked at seismic processing and then interpretation. And what you're looking at here is this chart are the different sorts of interpretive processes and applications that use machine learning. Fault detection was the number one, where 23% of the articles related to that. Lithofacies classification was 22%. And petrophysics and rock physics was 15%. Now on the right, what you see are the list of the various interpretation applications. And then what you see in the vertical y-axis here are the actual machine learning algorithms. Now I have further divided that. If you see a yellow, that means it's an unsupervised approach versus supervised. And if you see it, on my part, I misspoke there. The yellow represents neural networks. If it's underlined in red, it represents unsupervised approaches. So you can see the difference in the spread of things. Now, what you notice right off the bat is the convolutional neural networks are the dominant application. This is a deep learning supervised approach in machine learning to interpret data. Quite often, the dominant one in several categories of interpretation. Fault detection, which was the big one here, is absolutely dominated by convolutional neural networks, as you can see here. Now, the next lithofacies classification, it's got a little bit more distributed to different applications. Self-organizing maps, which is unsupervised, comes in there. A little bit more distributed in the different types of machine learning. And then the petrophysics and rock physics, it's distributed pretty good too, at least compared to some of the others, which are dominated by convolutional neural networks. So this gives you an idea of at least what publications we're talking about and applying it to various interpretation problems. But what's interesting about that is most of these, almost all of these approaches are applied to solve very specific singular tasks in a traditional interpretation workflow. In other words, fault detection, fault identification, horizon picking. It's very easy to isolate what algorithm is being used specifically for that interpretation workflow. And also remember, publication does not mean implementation. There's a lot of these different applications, but you don't see it used all the time in a routine fashion, at least not yet. Now, something that could have a tremendous impact on how we interpret our data, especially seismic data in the future, is full waveform inversion. And involved in that process is a lot of artificial intelligence and machine learning approaches. And I'm going to go over that with you. For those of you who don't know, full waveform inversion is a nonlinear data fitting procedure. And what it initially was proposed is to involve the whole seismic wave field. We fundamentally only use P-wave data today. But 𝗦𝘂𝗺𝗺 and 𝗦𝘂𝗺 back in the 80s initially devised a thought process to where you could actually go through and optimize your data to come up using the whole seismic wave field to get the results, as opposed to the way we do it today. And it's an optimization problem. In other words, you look at the discrepancy between the measured data and a synthetic data set that generated from some surface estimate is minimized. And I'm going to go through that process here shortly. Now, today, full waveform inversion is primarily employed as an effective tool for high-resolution velocity model building. And it employs the acoustic wave equation, or the acoustic FWI. You see FWI a lot of times when they're doing this. But it only accounts for the P waves. You say, well, that's not exactly what they proposed. That's exactly correct. They did not propose that in the initial definition of full waveform inversion. Well, but I'll show you where we're at on that. Now, this is a workflow, and I'm going to go through this on how full waveform inversion works. And it's very different than our basic fundamental processing flows that we use today. For example, here is the data that was acquired in the field. These are shot gatherers. And they use a wave equation approach, and they will use either some initial velocity, tomographic velocities, some initial information. They will model this information and come up with a set of shot gatherers and compare that to the real data. And they will see the difference between these. They'll look at the difference between these two. Now, in this process, at the very beginning, you get some sort of velocity information, whether it's our traditional tomographic methods, migration velocities, wherever you're getting it. But there are, I know I've edited and reviewed papers that are using some supervised methods to improve on this model initially, to get it closer to the answer, so you don't have quite as much compute power going into the whole flow. But once you measure the differences right here, then you measure the misfit. You use machine learning algorithms to understand how it's different, or how the misfit takes place. And once you've done that, you come up here and you use a lot of gradient-based optimizations on how do you go through and modify these misfits. And there can be hundreds and thousands of these things, filtering and weighting and muting, etc., trying to get towards the answer. And once you've done that, you go back, make another model, again, compare and measure the differences, and you do this over and over and over again until you have a global minimum on the misfit. And there you have the answer. Sounds simple, but it is not simple. It's extremely involved. But let me show you the reason there's a lot of excitement on full waveform inversion. Here's a typical tomographic velocity field on a vertical seismic display on a seismic line. This is west of the Shetlands. This is what an acoustic full waveform velocity model looks like. The difference is pretty dramatic. It looks like real geology. This is what's got people excited. Here's another example. Again, a typical tomographic velocity model used in processing. This is what 30 hertz acoustic full waveform velocity model looks like. Again, it's starting to look like real geology. Here's an example in the Alaminos Canyon in the deepwater Gulf of Mexico from Wang et al. And what you're looking at here is the typical velocity from tomography that we get. These are vertical seismic displays. And here we've taken that velocity in a typical processing using our advanced reverse time migration using these velocities. Here we have the acoustic full waveform inversion velocities using that same reverse time migration. And you can see it's a much better solution. It's a more accurate solution in a complex geologic setting. Here's another one where you're looking at the conventional velocity model here, and here they use reverse time migration at 20 hertz. Here is the acoustic full waveform velocity model at 11 hertz, and here's a much better reverse time migration version of that using these acoustic full waveform velocities. Again, it's getting us better results, just still using the P-wave information. But as I said, there's limitations to this. There's limitations to acoustic full waveform inversion. There are mode conversions at sharp boundaries. The true phase and amplitude requires a complete physical phenomena of the wave propagation. Cycle skipping, illumination issues are better resolved by the entire wave field. To get true reservoir characterization, you have to have the entire wave field. So what's evolving and where we're trying to go is to address these limitations with elastic full waveform inversion. And elastic full waveform inversion incorporates the entire wave field, the P waves, the S waves, converted waves, multiples. This was the idea of Tarantola and Laley at the very beginning, trying to incorporate the full seismic wave field. This is what elastic full waveform inversion is attempting to address. So here's some examples. Here's one in the deepwater Gulf of Mexico. What you're looking at here is reverse time migration with a typical tomographic velocity solution. Here is a reverse time migration, but this time we used an acoustic velocity solution. And here we're using the reverse time migration with the elastic. Now, these are different elastic full waveform velocities. And here is where we're trying to go. This is the solution with the elastic full waveform inversion, but reflectivity. There's no migration involved here. You've gone through this optimization process over and over and over until you've gotten to the point that you have the final result without migration. Just absolutely phenomenal where this is going. Here's an example. This is from McLennan et al. From Doug. And here's a reverse time migration using conventional velocity modeling. Here is a reverse time migration using the elastic derived velocity model. And here there is no migration. It's using the raw data sets as input, going through the optimization process and the elastic full waveform imaging in this case. Absolutely giving us the best results. And this is actually tremendous. This is a high resolution data set that was shot in the Johann Castberg field in the Barents Sea. And if you look on the bottom left, you're looking at the velocity from the 90 hertz elastic full waveform inversion. Very detailed. If you look at these arrows, you're trying to see the gas-oil contact and the oil-water contact. Now, this is Kirchhoff pre-stack depth migration using the elastic full waveform inversion velocities. Very nice. But if you go all the way through to get the elastic full waveform inversion reflectivity, it's even better. But what I want you to see on these upper two, this is a time slice right at the gas-oil contact right there, that upper arrow. And this is actually the Kirchhoff pre-stack depth migration using that. But what you're looking at here, this is the velocity field from the elastic full waveform inversion. The velocity is actually seeing the contact. That's pretty impressive. It's actually seeing the contact, the gas oil contact. This is velocity. But this is not all a panacea. And the reason is you need low frequencies to avoid a lot of these cycle skipping issues. You need to have some very long offsets to record turning and diving waves. We need to get this in the data, get these low frequencies. We need very ultra long offsets in a lot of cases. And in some cases, these ocean bottom nodes or sparse node surveys literally are out as much as 30, 40 miles trying to get these long offsets in these diving waves to get the best solutions. And so this is very promising, but obviously we just can't do this everywhere. So what's the largest barrier to full waveform advancements? Well, obviously some of it's acquisition, but I think at least in the marine environment, that's being addressed to a large degree of ocean bottom nodes, ocean bottom systems. Onshore, we haven't seen it as much, but Saudi Aramco actually has done some work onshore with some very promising results. But what is the largest barrier to full waveform inversion advancements? Computer power. This thing takes a tremendous amount of computer power for full waveform inversion. In fact, Dave Monk, in his distinguished lecture tour, indicated that if I have full waveform inversion at 2 hertz, however long that takes, the same procedure at 64 hertz requires about 1 million times more computational effort. This is the scale of what we're talking about. And we've had great advancements, I think, in the last 5 years in the application of a lot of acoustic full waveform inversion and elastic full waveform inversion. A lot of it's been selectively employed in some of the largest fields, especially a lot in some of the subsalt fields. But this requires really high performance computing systems or supercomputers to do this. And we really need that, at least at the state of where we are today, to get these things processed. These things take a long, long time to process, and they're obviously very expensive at this point. So given that, what's the role of computer power in advancing geoscience technology? And of course, the computer power affects everything we do, but looking at it purely from a geoscience perspective, as we talked about these supercomputers or high performance computing, they use clusters that consist of hundreds or thousands, and should I say millions of compute servers that are networked together. Each server is called a node, and these nodes are clustered together and in parallel, and this boosts the processing speed that give us our high performance computing capabilities. Now, there's a company called Top 500 that every year goes and evaluates the fastest supercomputers in the world. And as of June of 2024, these are the top 5. I don't expect you to read those numbers, but the second, the runner-up is 1.353 exaflops. Well, what's that mean? That's 10 to the 18th is exa. That's a quintillion calculations per second. So it's a little over a 1.353 quintillion calculations per second. And this is by the Oak Ridge National Laboratory. But the winner, at least as of June, is from the Lawrence Livermore Laboratories, 1.742 exaflops, or 1.742 quintillion calculations per second. And I want you to notice something. It has 11 million, either CPUs or GPUs, 11 million. Now, there have been several companies that have vowed that they were going to reach 2 exaflops by the end of 2024. I don't know if they have yet. but they probably have it because we're going very fast, or at least as fast as they can go at adding these CPUs to get these speeds up. Now, the cloud, which is interrelated in a lot of cases with these high-performance computing, as we know, is a bunch of servers that are accessed over the internet, which has software and databases that we access and run. Now, these cloud servers are located in data centers around the world. It's actually very difficult to get an exact number. As of right now, the estimate is about 11,000, but it's probably eclipsed that since I actually put this together. And today they say, and I think this is really based on last year, 20% of the global data centers are used for AI. Probably more than that now, and I can almost guarantee that it's more than that now. And the challenge here is that these data centers right now are pretty much universally thought of as using 1 to 2% of the world's power right now. 1 to 2% of the world's power, and they're approaching 3 to 4%. Some people say by the end of the decade, some of them will say it's coming much, much faster than that. And of course, so the reason for a lot of that is the HPC computing in the cloud. That's what's doing it. There's a reason why the cost for these things and these data centers are growing, and they're starting to put these data centers in areas around the world that have access to power. It requires that power. There's a reason NVIDIA ended up being, I'm not sure if they are today, but were the largest company in the world by market cap, because they make GPUs used dominantly in machine learning and especially in LLMs. And these are obviously some of the people who are directly involved in these data centers around the world. That's all nice, and it's kind of where we are today. But there's an elephant in the room, and if you're not familiar with that term, there's something else that's looming over the horizon that will potentially change everything, and that's quantum computers. Many experts indicate that within a decade, quantum computers will be fundamentally operational. Now, quantum computers are operational right now, but they don't do anything yet. It's that their full capabilities hopefully will do, and because there's a lot of issues related to them, which they're trying to resolve. So what is quantum computing? Well, it's based on the laws of quantum mechanics. And what they're doing is they're taking advantage of how physical matter exists and the properties that it has at subatomic levels. And that's different than in our obviously normal way of life. These subatomic levels of physical matter have both particle and wave properties. And what they're trying to do is take advantage of that in building these computers. And as we know, classical computers use bits, which are 0 and 1, but quantum computers employ qubits. A 0 or 1 are a superposition of both. And 500 qubits can represent the same information as 2 to the 500th power normal bits. 2 to the 500th power. Think about that. And this enables, obviously, these multi-dimension, huge quantum algorithms to be applied. And the increases in our computational, even in our fastest supercomputers, can be exponential to millions of times faster. The potential is quite dramatic on what this potentially can do and bring to the table. And there's an intense competition, obviously, in governments and companies around the world trying to develop these quantum computing capabilities. But there's also a lot of people looking at this on how to deal with these quantum computing algorithms once they start evolving in computers. Because once that becomes operational, they can very quickly break every security code in the world. So obviously we have to deal with that. Again, very, very exciting, and a lot of money being thrown at this for good reason. So what type of quantum computer will lead the race for the future of computer power? Well, I don't know. There's a lot of contenders. There's a lot of companies. Most of these quantum computers today are working at several hundred degrees below zero because subatomic particles are more well behaved at those temperatures. We don't know. Every day you'll hear different advances by various companies in these various quantum computer developments. Time will tell, and we'll see how that evolves. My last slide is related to, this is my idea of an interpretation workflow of the setting, the environment that we might be in the near future. There may be 5 years, it may be 10 years, it may be 20 years, I don't know. But this is kind of my vision of what might happen. Again, everything is up in a cloud running on quantum computers. Speed or power is dramatic because quantum computers are now operational. That's where all of our data is. That's where all of our algorithms are. And it's all interfaced with large language models. That's how we have agents that attach to these, and that's how it interacts in this whole interpretation process. Machine learning, we're going to see automated workflows. You're not going to be doing these single tasks of interpreting faults or a single task of interpreting horizons. This is going to be automated and gone through in a very sequential, not even sequential, calculation of these different algorithms to come up with our interpretation results that we're looking for. You're going to see various machine learning methods. This is already happening to be combined. Large language models by themselves now have at least 4 different sorts of machine learning applications involved in them now. Modeling, you can imagine what we can do with the modeling and digital twins, 4D surveys, the details and what we can do with almost unlimited computer power can be quite dramatic. And of course, that's going to get us to what we're looking for. Rock physics models, pore fluid models to understand the elastic properties of the Earth and understand the geology, to truly understand not only the Earth, but the fluids in the Earth and how they move and how we can find and produce them. So with that, that's the end of my talk, and I'll be glad to take any questions.
Well, I have a question for you, Rocky. There's been some recent work, as you know, in applying unsupervised machine learning techniques to predict lithologies. Could you speak to that?
Sure. I mean, one of the things that the machine learning brings to the table is the ability to, as I indicated earlier, is understanding or seeing nonlinear relationships in the data. And there are been attempts, and as you saw, there were several algorithms that were people had written papers on using machine learning to look at lithologies and things like this. Well, machine learning is absolutely geared for that sort of thing, and because it can understand the nonlinear relationships. And when you look at lithologies and the impact of things like the fluids in the lithologies, the various parameters in the lithology, these machine learning algorithms are absolutely suited for that sort of thing. And we've seen several results that have been quite impressive in correlating or identifying, I should say, various lithology variations. And it can vary, carbonates, clastics, doesn't matter. There's no preference on that. It's just a matter of the inputs at the very beginning.
All right, good. Thanks for that. We've got a couple of questions coming in. Rustam asks, what do you think? Who do you think are the leaders in AI/ML geoscience? And I'm inferring from the question, Rustam, maybe companies that are the leaders.
Well, that's a loaded question. Well, there are several people, and I don't know that. Uh, I don't want to comment on the companies. I know that if you look at the specific types of machine learning that are being used, there's no question that convolutional neural networks have taken the large bulk of the applications being used for geoscience. And that, again, that's a deep learning supervised method. It's based on image processing. And that's why it's very, very good for faults, as well as some other applications. But I think a more fundamental question is the application of unsupervised versus supervised learning. These LLM models, a lot of people don't know a lot of the details, and it's evolving, because I certainly don't know all the details either. But it initially started with unsupervised learning, or something called self-supervised learning. And that's the dominant part of these LLMs. And now other component of it is the interface between the humans and the results. A lot of those get into some supervised applications, and even reinforcement learning starts to come into play. They're actually using several different types of machine learning. So depending on what you're trying to solve, it can dictate the answer to that.
Okay. Antoine asked, how important would data management be to enable the application of these technologies? The importance of data management.
Well, it's actually they kind of go together. I've seen there was an APG AI ML forum right before Christmas, and that was several presentations dealt with data management, how to deal with that, man. I mean, when we don't exactly understand all the data we have to even analyze, if all of a sudden you did, then who knows what might happen, and have access to it and be able to apply that in an efficient manner. Who knows what kind of answers might come up out of the whole thing.
Okay, good. Carlos asked a very specific technical question. What is the vertical and aerial resolution of 𝗦𝘂𝗺𝗺, elastic full waveform inversion, derived reflectivity, and how do these depend on the signal to noise and frequency of the input of the recorded data?
All of that is taken into the process. I mean, if you think about this, it's got noise, it's got multiples, you got converted waves, P to S, S to P, everything that's in our data that we normally get rid of. We process all that out. It takes all that information and it looks at it and tries to modify the misfits. And the magnitude of the amount of variations that are being modified to get you closer to the answer. That's why there's so many iterations involved. That's why it takes a long time, millions of iterations, to come up with the optimization solution that gives you the global minimum misfit. It takes all that into consideration. But you got to remember now, if you went all the way to the imaging or the reflectivity and you're not doing migration, it's got to go through all these iterations to get all the data in its right spot, and not using migration algorithms. I mean, that's why we don't have a lot of this done yet. It's in its infancy, really.
Another question on 𝗦𝘂𝗺𝗺. Jonathan asked, can we look forward to lithotype classification as part of 𝗦𝘂𝗺𝗺?
I sure hope so. I absolutely think that's going to happen, and because it's going to get us closer to, in my last slide, it's going to get us closer to this quantitative interpretation of all these parameters, which is what we're trying to figure out, we're trying to understand, because we're using everything in the data. And so I'm quite excited about this. We're not there yet. The computer power doesn't allow us to be there yet. But I feel more, well, the process of the optimization process, it can be quite involved. And I fully don't understand all the details and all that, because that's really the process. Each of the processing shops have their own slant on how they're doing this. But the potential of this is, to me, is quite dramatic. And I'm pretty, being a geophysicist and been around for a while, I'm pretty excited about this and the potential of it anyway.
Ben asked a question about preparedness. He says, what do you recommend geoscientists do today to better prepare for the upcoming quantum computer age? The skills that people may need.
Well, I think at least from my perspective, what the quantum computing is going to do is it's just going to be a fast computer. Now, this is me I'm not a quantum computer development expert by any means. I'm not sure the limitations yet. You're going to start hearing words like entanglement, coherency. Things can be very unstable in the subatomic world in the development of these quantum computers. That's what they're trying to address. And I think that again, the evolution of these quantum computers, once they start coming, you're probably going to see a hybrid, a mix of quantum computing and normal computing and our conventional computing. And then it'll probably ultimately, as it gets more and more evolved, maybe it'll go to a total quantum computing solution. I don't know yet. Who knows exactly what's going to happen? All I do know is that the potential of quantum computing to take us way, way faster than anything we're doing today.
Yeah, Carlos also asked a question about the power requirements for quantum computing, and I think that too is unknown, given the fact that most of these computers today are basically research machines.
Right. That's exactly right. We just don't know. I would suspect it's a lot just guessing, but I don't know. Who knows? I'm sure these quantum computing experts know.
Oh, sorry. A follow-up to that, do you know of any initiatives around the world that are using full waveform inversion on quantum computers?
I don't know of any. I don't think there's any. Well, I may be wrong. There probably are some things being done with quantum computing that are starting to get more advanced. Most of the applications I've seen are pretty simple things that our normal computers can do already, but you're taking small steps at the very beginning here. And I look at it from a geoscience perspective on what we can do when we don't have a lot of computer power limitations, which, for example, in full waveform inversion is absolutely an issue. So we'll see. We'll see how it evolves.
Yeah, Ahmed's got a question also related to the career of geoscientists, given what you've laid out today. What do you see the impact on geoscience careers in oil and gas or in industry in general, given these developments?
That's a good question. And my opinion is that, people talk about how artificial intelligence and machine learning are going to take the jobs away of geoscientists. I think it's absolutely incorrect. I think it's going to open, I guess in my career, because I've been around so long, every time a new technology evolves, for example, 3D surveys, the thought was, oh, we don't need interpreters. We got 3D surveys now, and these workstations will solve it. It enabled us to do more than we could ever do before. That's what this is going to happen, I think. It's going to enable us to do things we never thought of before. But I do think that in the future, if you're a geoscientist, if you're not aware of machine learning and not have a feel or an understanding of the types of machine learning that and what they can do from an interpretation standpoint, I think you're going to have trouble. But I don't worry about that with the young generation, because you've grown up with this stuff. You see it all the time. And to look at this and incorporate it potentially in your workflows, I think actually very exciting. No matter what you're doing in the subsurface evaluation, whether it's looking for oil and gas, geothermal, you name it, it's going to affect everything.
Indeed it is. And we are close to the hour. I want to respect everyone's time. If you don't mind, Rocky, let me just show one more slide so
Sure.
that people have an idea where to, sorry about this, where to get some information on what we've presented today. And I will just put this in full screen mode. On the slide are my contact details. You probably received an email from me, but just in case you need this, you're welcome to email me for additional information on some of the things that Rocky has spoken of today. You can also text me. Feel free to text me or contact me on WhatsApp on the mobile number here. Did get a question about the slides. A video will be available next week on the resources page of geoinsights.com, our company site. Please check it out. This will be the first item there in the upper left-hand corner as you go into the resources page. So we invite you to visit that material. There's also a tremendous number of technical papers and other webinars there, and you're welcome to check those out. We are still planning our next webinar, which we try to do quarterly. So please look for an invitation from me sometime next month for a March webinar. Topic to be determined, but we always like to have excellent speakers such as Rocky today. And with that, we want to thank you again for your time and interest. Please, again, feel free to email me or contact me on mobile or WhatsApp if you've got questions about Rocky's content or about the Paradise AI Workbench for reservoir characterization. Have a good day.